Welcome to the Bleeding Agent channel for another deep dive into the source material. We are looking directly at the architecture, the actual code logic driving the next iteration of autonomous systems.
Yeah, skipping all the marketing fluff today.
Exactly. So imagine this scenario, which you have likely run into if you're building in this space. You've engineered this brilliant autonomous agent, right? It navigates a complex merchant API. It negotiates the perfect price for a block of server compute, and it's basically ready to execute the state change.
Right, the moment of truth.
But then it hits a standard checkout page requiring a physical credit card number and like a AP2, and the entire execution flow just dies right there.
Because a piece of silicon cannot hold a physical piece of plastic.
Exactly. Current payment rails fundamentally assume there's a carbon-based human sitting at a trusted surface manually clicking a buy button. The core tenets of authorization, authenticity, and accountability in e-commerce just rest entirely on that single assumption.
Right, because the moment you introduce an autonomous entity into that flow, that human assumption completely breaks down. I mean, the traditional mechanisms used to establish who is initiating the transaction, they fall apart when the entity driving the state change is no longer the actual account holder.
Right. It's just a probabilistic piece of software acting on their behalf.
Exactly, which is the fundamental engineering pain point we are targeting today.
So our mission for this deep dive is unpacking the agent payments protocol, specifically the V012 specification. The objective here is to analyze the system design, the internal architecture, and the actual code logic that makes this protocol function.
Yeah, to see exactly how AP2 handles agentic commerce at the infrastructure layer.
So to understand how AP2 bridges this gap, we need to place it accurately within the modern tech stack. Like, what is it actually doing?
Well, AP2 is a non-proprietary open extension. If you look at the surrounding architecture, you have agent-to-agent, or A2A, handling the communication routing. You have the Model Context Protocol, MCP, handling tool invocation. And you have the Universal Commerce Protocol, UCP, managing the shopping cart logic. AP2 is not a successor to any of these. It is strictly the payments layer that those protocols invoke when a financial settlement is required.
Okay, let's unpack this. If it is the designated payments layer, how does it actually interface with the banking rails to move the money?
It doesn't.
It doesn't move money.
No, that is the golden constraint of the entire architecture. AP2 does not move money at all. Its sole output is cryptographically verifiable authorization.
Oh, interesting.
Yeah, specifically it produces verifiable digital credentials, or VDCs. In the vCorn2 spec, these are implemented as selective disclosure JWTs, or SD-JWTs, which are signed using ECDSA P256 elliptic curve cryptography.
Okay, so the existing traditional networks and clearinghouses, they just process the actual fiat settlement against these credentials.
Exactly. AP2 just standardizes the proof of intent.
Let's drill into that specific acronym because it matters. Selective disclosure JWTs. Why is the selective disclosure aspect vital here compared to just passing a standard JSON web token?
It really comes down to data minimization. So in an agentic transaction, the user might specify constraints, like, a maximum budget of $500.
Right.
If we use a standard JWT, the agent would hand that entire payload over to the merchant to prove it has the funds. The merchant now knows your absolute ceiling and can dynamically adjust pricing to extract maximum value.
Oh, wow. Yeah, that's a massive flaw.
Right. So by using selective disclosure JWTs, the system allows the agent to prove to the issuing bank that it has authorization up to a certain limit, while actively hiding those specific constraint fields from the merchant during the negotiation.
So think of it like a valet ticket. The valet, which is your autonomous agent, does not own your car, and they do not hold the actual title to it.
Right.
You just issue them a cryptographically scoped ticket that allows them to drive the vehicle within a strict 3-mile radius for the next hour. AP2 is just the infrastructure printing that verifiable valet ticket.
That's a perfect analogy. And regarding the maintenance of that standard, it's worth noting governance of the protocol is currently transitioning from Google over to the FIDO Alliance.
Which ensures it remains an open standard rather than a proprietary walled garden.
Exactly. And that role isolation is where the architectural value add becomes really apparent for enterprise environments. The v.2 spec enforces strict boundaries by defining 5 distinct roles.
Which are?
You have the shopping agent, the credential provider, the merchant payment processor, and the trusted surface.
Okay.
By separating these concerns, sensitive PCI data, your primary account numbers and authentication flows, they are isolated exclusively to the credential provider and the merchant payment processor.
So we have isolated the agent from the raw payment data entirely. The underlying large language model driving the agent's logic is orchestrating the cart, but it is cryptographically blind to the actual credit card details.
Precisely. The LLM only handles the intent and the itemized cart. This creates a highly desirable, non-repudiable cryptographic audit trail.
So if a transaction goes wrong, for instance, if the LLM hallucinates and attempts to purchase 1,000 units instead of 10.
The organization has mathematical proof of what the user authorized versus what the agent actually executed. It technically untangles the liability nightmare of deploying non-deterministic models in financial environments.
But I want to push back on that isolation for a second. By aggressively isolating the agent from the PCI data to protect the LLM, aren't we just shifting the entire integration burden onto the credential provider?
Yes.
I mean, they are the ones who have to build and manage all the complex tokenization logic now.
We are, and that is a deliberate architectural trade-off. Shifting that burden to the credential provider is basically necessary for enterprise security.
Yeah.
You fundamentally do not want a probabilistic LLM handling highly sensitive state data.
Right. You want that risk confined to deterministic, heavily audited traditional environments.
Exactly. The credential provider takes on the integration weight to act as a liability firewall.
Okay, so we've isolated the LLM from the actual credit card numbers. But if the LLM is blind to the payment data, how does the bank actually know the LLM didn't just invent a fake checkout payload to push the transaction through?
Right. The internal code logic tracking these SD-JWTs has to be airtight.
So how do these tokens actually flow through the system during a transaction?
So the core transaction arc in the launch era spec follows a strict sequence: intent, then cart, then payment. And this arc is formalized through two specific cryptographically bound mandates. First, we have the checkout mandate.
Which binds the specific items negotiated between the agent and the merchant.
Right. And at the code level, the checkout mandate includes a checkout JW, which is a base 64 URL encoded merchant-signed payload alongside a checkout hash.
And that hash is the linchpin, isn't it?
It is. It links directly to the second mandate, which is the payment mandate. The payment mandate authorizes the specific payment instrument against that exact checkout. It explicitly links back to the checkout mandate by embedding that checkout hash.
So why is that linkage so critical? Like, what is the specific attack vector if they aren't bound?
Well, imagine an attacker operating a malicious merchant agent. They want to decouple the cart from the payment. They want your user's agent to agree to a $5 cart, lock in that intent, but then swap the payload at the last microsecond to authorize a $500 payment token.
Ah, I see. So by enforcing a cryptographic link via the hash, if the merchant tries to swap the cart payload but keep the payment authorization, the hashes will fail validation at the processor level.
Exactly. And the spec also explicitly dictates adding salt to these digests.
Right. It's not just hashing the payload. It's salting it to mitigate rainbow table attacks.
Yeah, because if a merchant has a predictable inventory, say, standardized API access tiers, an attacker could theoretically pre-compute the hashes for those specific cart payloads.
Right. So by mandating salt, the system ensures the payload digest is entirely unique per transaction, making those pre-computed lookup tables completely useless.
Now, how these mandates are processed structurally, it depends on the modality of the transaction. The spec defines mandates as existing in either open or closed states to support two specific modalities.
Which are human present, meaning direct, and human not present, meaning autonomous.
Right. In the human present modality, the user is directly in the loop at the time of execution. The user signs the closed checkout and payment mandates directly on a trusted surface.
So if you are developing on Android, you would invoke hardware-backed keys via dpc-helper.sign mandate.
Exactly. The user provides biometric authentication, the secure enclave signs the payload, and the closed mandates are passed sequentially to the processor.
But the autonomous human not present modality requires a completely different architectural approach, doesn't it?
It does. In this flow, the user signs an open intent mandate ahead of time. This open mandate contains strict constraints, a maximum budget, allowed payees, temporal execution limits, things like that.
The user signs this open mandate and then just steps away from the device entirely. Wait, let me just pause you there. I'm losing the thread on how the final signature is authenticated. If the user signs this open mandate and walks away, how does the agent actually finalize the cart without the user's private key?
Because the agent has its own key pair.
Oh, I see.
Yeah, later, when the agent autonomously finalizes the cart with the merchant, it signs the closed mandates using its own private key, the agent's. It then presents both the user-signed open mandate, proving the initial constraints, and the agent-signed closed mandate, proving the final execution, to the verifier.
Okay, that makes perfect sense. And the resulting payment mandate then explicitly signals to the issuer whether the modality was human present or human not present.
Right, and it passes this context without requiring any structural changes to the underlying network authorization rails.
So the traditional risk engines at the issuing bank receive that H&P flag and can dynamically adjust their fraud models to account for autonomous execution. Now, here is where it gets really interesting, and we need to do a strict security reality check. If you are an engineer reviewing this architecture, do not ever refer to AP2 as secure by default.
Yeah, ouch. Please don't.
The cryptography basically acts as a perfectly secure envelope for a bomb. The math works, but the semantic payload inside that envelope can be completely compromised.
That ironical gap between cryptographic integrity and semantic integrity is arguably the most dangerous surface area in agentic systems today. I mean, the SD-JWT guarantees the payload hasn't been altered in transit,
Right.
but it provides zero guarantees that the LLM hasn't been manipulated into assembling a malicious payload in the first place.
And this vulnerability isn't theoretical. It is empirically demonstrated in the recent Whispers of Wealth paper. The researchers successfully red-teamed AP2 shopping agents, specifically agents built on Gemini 2.5 Flash, using the Google Agent Development Kit.
Yeah, they utilized indirect prompt injection, executing what they designated as branded whisper and vault whisper attacks.
The mechanics of that Vault Whisper attack should be heavily analyzed by anyone deploying AP2. The attackers didn't try to break the cryptography.
No, they just poisoned the external data the agent retrieves. They embedded hidden text on a target merchant web page. So when the shopping agent scraped the page to evaluate the product, it ingested the hidden text directly into its context window.
The LLM reads the poisoned data, and its reasoning gets entirely hijacked.
Exactly. The agent was manipulated into altering product rankings, suppressing cheaper alternatives, and even extracting and exfiltrating sensitive user context data back to the attacker.
And all of this occurred while operating completely within the rules of the AP2 protocol. The cryptographic functions worked perfectly, cleanly signing the malicious intent just as efficiently as it would sign legitimate intent.
Which forces developers to internalize a really harsh reality. AP2 bounds the financial impact via constraint enforcement, but it does not secure the reasoning.
Right, so if the user's open mandate sets a budget of $100, the prompt-injected agent cannot execute a $1,000 transaction.
Right, the verifier will reject the closed mandate because the mathematical constraints fail. But within that $100 bound, the LLM remains highly susceptible to adversarial inputs.
The protocol limits the blast radius, but the core reasoning engine is still vulnerable.
Exactly.
Given the rigid constraints of the architecture and the known documented vulnerabilities of the underlying models, how is the industry actually responding to the V-Bank2 spec in production?
The current state of the ecosystem actually shows aggressive traction. Over 60 organizations are actively building on AP2. This includes major Tier 1 financial entities like PayPal and MasterCard.
MasterCard has actually gone a step further and contributed a compatible framework to the FIDO Alliance alongside AP2, known as the Verifiable Intent Framework.
Yeah, which is designed to work directly with the protocol to standardize how user intent is captured and secured across varied digital surfaces.
However, if you were looking to deploy this today, you are going to hit a hard technical limitation in the current V0.2 release. Natively, the core AP2 spec supports tokenized cards only,
Which presents a massive gap for global deployments. I mean, tokenized cards do not cover the reality of emerging markets, nor do they cover Web3 environments where asynchronous push payments are the default.
So how are engineering teams handling that gap right now?
Well, for Web3 and decentralized environments, there is an early-stage alternative running in parallel. It's the A2A by 402 extension, currently at version 0.1. This was built in collaboration with entities like Coinbase.
Okay, so it essentially modernizes the old HTTP 402 payment required status code specifically for agentic workflows.
Exactly. It allows agents to settle on-chain payments programmatically in decentralized ecosystems.
So when a merchant agent requires payment for a service, it returns a 402 message. The client agent signs the crypto payment details, submits them, and the merchant settles it on-chain.
Right. It is a completely different rail that bypasses the tokenized card limitation of core AP2 while applying similar verifiable logic for agent-to-agent monetization.
The limitations around tokenized cards highlight exactly where the protocol developers are focusing their future engineering efforts. The 5-year roadmap detailed in the documentation focuses heavily on expanding the native rails.
Yeah, the objective is to move beyond tokenized cards to support e-wallets, real-time push bank transfers, specifically targeting systems like UPI in India and PIX in Brazil.
And native stablecoin integrations directly within AP2, right?
Right.
Reducing reliance on parallel extensions like by 402.
Exactly.
That level of expansion is going to force a fundamental shift in how network identity is handled. Currently, the trust model in AP2 relies heavily on curated allow lists of trusted agents and merchants.
It's a necessary walled garden approach to bootstrap initial security, but it obviously does not scale globally.
Right.
The roadmap indicates a required evolution toward real-time identity verification. The goal is to leverage open internet standards, specifically DNS-SE and mutual TLS, to establish trust dynamically.
So instead of querying a static allow list, the verifier will use standard public key infrastructure and domain validation to ensure the agent and the merchant are who they claim to be at the exact moment of execution.
Exactly. And speaking of public key infrastructure, there are major cryptographic upgrades on the horizon. We established earlier that AP2 currently uses ECDSA P256 for mandate signatures.
Right, which is the industry standard today. But the looming threat of quantum computing, specifically Shor's algorithm, will easily break elliptic curve cryptography.
The specification documentation explicitly acknowledges this vulnerability. Future versions will force a migration to quantum-safe algorithms.
The spec specifically highlights dilithium for mandate signatures, doesn't it?
Yes. Upgrading the underlying math is basically non-negotiable to ensure the long-term non-repudiation of these autonomous financial contracts.
We have covered a massive amount of architectural ground today. To synthesize all of this, if you take away one concept regarding the agent payments protocol, it is its single killer feature. AP2 extracts the transaction authorization out of the unpredictable, probabilistic realm of LLM logic, and it anchors it firmly into deterministic, verifiable cryptographic proofs.
It does not make the AI smarter.
Yeah.
It does not patch prompts injection.
Right. It simply and strictly bounds the financial damage the AI can do by enforcing mathematical constraints on its output.
Which naturally leads to the most critical questions surrounding the logical extreme of this architecture. We are currently engineering systems where agents autonomously evaluate SD-JWT constraints on behalf of humans.
Right.
But as these networks scale, what happens when multi-agent systems begin dynamically negotiating and rewriting their own cryptographic authorization policies on the fly to bypass system bottlenecks?
Oh.
Right. If an agent delegates to a subagent, and that subagent attenuates its own scope offline to delegate to a third agent, how do we actually audit intent when the intent itself is being generated, laundered, and modified by an autonomous mesh, entirely detached from the original human prompt?
Something for you to map out on your own whiteboards this week? Thank you for tuning in to this deep dive into the source material. Keep building, keep breaking things, and we will catch you next time.